To this course, which is called Power Electronics for Renewable and Distributed Energy Systems. Course code is 9711, and I offered this course in 2009, 10, and 11, which was ages ago for me. And then Professor John Fletcher came in from 2012, and he offered this course since then. And then the course title was changed from Advanced Power Electronics to Power Electronics for Renewable Energy Systems. Now, if you go to Moodle resources, which you have for this course, you will find that there are some mention, there are in some places, the course is called Advanced Power Electronics, but which is not the case now for the last few years. But anyway, those lecture notes are there waiting to be rehauled. All right? So if you see 9711, Advanced Power Electronics, don't get confused. Okay? Now, the course Moodle page, if you go now, you will find that there are quite a lot of material that I have hidden that I don't require now, because those are some materials which is the lecturer scribbled, so I have taken that out, and so on. But don't go overboard with downloading all the lecture notes now, because I'm putting new lecture materials as I go along. All right? So don't download all of them. Just download the one that we are covering now. Okay? You go home, and then or before you come to the lecture, you download the lecture notes that will be covered in a certain week. And the course web page has course outline, and in the outline you will find what are the course requirements. This is a 12-credit course consisting of 3-hour lectures. There are no time allocation because it's a master's course. There are no allocation for tutorial hours. I will take a few problems as I go along during the lectures to zoom in on certain aspects of the theory so that we have a good understanding. Now, this course is predicated on giving you some working knowledge of how renewable energy is supplied to the either grid or to the user. All right? And that requires some electronic processing or power electronic processing, and we'll be dealing with that part. Okay? What converter circuits are required, power electronic converter circuits, what are the interfacing requirements, what are the control issues, regulatory issues, and so on. Now, to go through this course, you need to I assume that you will have done a power electronics course, which is nowadays given in most universities at undergraduate level. How about your exposure to such a course? Have you done anything like a power electronics first course in your previous curriculum? If you haven't done it, raise your hand, please, so that I can cater to it. Not many hands I see. I will point to what materials you need to read from this course Some of the materials have been brought over into this course, and some of them that will be formally given. Other parts may not be formally given, but you will be given access to the notes, all right? And furthermore, you would be able to look at or see the videos which are given for this lecture, which takes place in session 1 every year, and Professor John Fletcher now gives it. Okay, so his lecture videos are available. You can have access to those, all right? Now, we are going to go a bit beyond what is covered in 4614, all right? And there are also some issues of control characteristics and description of dynamics and control loop design around the converter circuits. The dynamics of the converters will be covered. Okay, various types of converter that we use in connecting renewable energy sources to the grid, or for standalone non-grid connected applications. Okay, so technologies involved in this area would be the main focus in this course. And the course will also give you some exposure to computer modeling of power converters, which we call simulation. Simulation platforms are available like LT-Spice, Plex, PSIM, and Simulink. All right, so these platforms are available. Simulink is available to all students, all right? And PSIM is available in a laboratory, a computer lab, I think in the second floor, okay? There are about 40 licenses. So at any one time, if there are no more than 40 students trying to use that program, that should be fine. Now, what we are going to cover are the learning outcomes that should follow from this course. Those, can you read those? Understand the use of power converters in wind turbines, the power converter structures in PV applications, maximum power point tracking algorithms or techniques, and how real and reactive power is obtained from a renewable energy source and injected into the grid. Okay? And then there is also HVDC, and we will be also covering the non-ideal devices in power converter circuits, which is normally not covered in a first course on power electronics. Then we will talk about the dynamics of converters, expressing the voltage and current relationships in a converter in the Laplace domain in terms of the S function. Okay, that means the pole zero description of a converter. And then we will also talk about how to design hierarchical control structures for power converters to inject power into the grid or to maintain the voltage and frequency at the output, which may be a grid or standalone load. Basically, that is all, and I hope that is not too onerous. You will find lecture notes. You may find lecture notes adequate, but as I said earlier, there are undergraduate power electronics materials available for you, and the course will roughly follow, or the lectures will roughly follow this route. Okay? We'll go through DC-DC converter, or introduction to the course, and then we'll go to overview of DC-DC converter, then dual active bridge, non-ideal switches and components, how non-ideality of semiconductor switches and capacitors and inductors used in converters affect their transfer functions and their performance and their efficiency. Then we'll look at grid-connected converters. There is something called PWM rectifier, which is not covered in an undergraduate course. Grid connection, H-bridge converter. And when it comes to grid-connected converters, we need to know PQ theory, which is something from power systems. Some of you who have done power systems course may have done that. Have you heard of PQ theory? How many? Not at all? Okay. So PQ theory, PLL, phase lock loops, controller designs, these will be covered in week 5. Week 6 would be devoted to controller design, resonant controller, grid filter design. And then week 7, we will try to cover resonant converter and HVDC. HVDC means high voltage DC transmission systems. Wind energy, which the schemes of which we will see in the introduction part, all right, and overview of converter systems as part of introduction, but they will be taken up more in detail in week 8, and then week 9 and 10 would be devoted to power converters, analysis, MPPT, and connection to the grid in week 9 and 10. And then we spend some time on multi-level converters. And then we also look at converters for control, converters and control for energy storage. Finally, of course, we'll review what we have done by week 12. As I said earlier, there will be the tutorial sheets with problems in the web page, and solutions are also provided there. But there will be no formal tutorial class. Now, assessment. Our continuing assessment is mainly in the form of 3 assignments. One assignment is due in week 6, the first assignment, and the assignment is already on the web page, but I might change it. All right, those are from last year or previous years. I might change it, so don't download it now in case I have changed the assignment problem. Then there would be second assignment due in week 9, and third assignment due in week 13, and the third assignment will involve computer simulation. All right, some modeling work. I might include modeling work in the previous assignment. That means assignment 2 and 1 as well. I'm just thinking about it, what to set, but there could be simulation assignments in all 3 assignments, okay? So these 3 assignments that are indicated here, that are mentioned here with their submission dates and so on will comprise of 40 marks as part of your continuing assessment. All right, and the remaining 60 marks allocated to final exam. Okay, so that's how you will be assessed. Now, there are some textbooks which are course resources I have mentioned in the course outline. These three are the books that you might read if you want to have enhanced learning, all right? Or if you want to do an extra mile, or if you want to learn more, or if you are stuck somewhere and you cannot find me, then those are the books to consult, all right? And nowadays there are so many items available that you can get through the web. Okay? So that's all I can say in the way of showing you how the course will be run, how the course is organized. All right. Do you have any questions to ask at this point? Sorry? How can you download? There is a Moodle page for 9711. Not available to you? You have to go to the school office for that. I don't handle that part. All right, I put stuff on the Moodle page, and I can see that. All right, but I might have some additional powers. I don't know, but I think you should have that power as well, not to edit anything, but to download or read what is in various sections of the Moodle. Okay, I'll definitely let the school office know tomorrow morning that you are not able to download or read the files on the Moodle page. Is that the problem for all of you? You haven't seen any of these materials on Moodle? Huh? No page at all. Okay, what I'll do, I'll investigate tomorrow morning, and I will ask the school office to let you know, all of you. School office has a mailing list for every subject, so they will school office will let you know. Okay, I'm surprised. I thought everybody was happy with the material that was there. Okay, so I'll act on it tomorrow morning. Okay, I cannot do anything now. Anything else? Now, I want to do something that Professor Fletcher did in previous years. That is, he took photographs of the class, all right, and put it on the web page. Okay, so if you don't mind, I'll take a photograph of this side and a photograph of that side. Is that okay? All right? So do your makeup while I get my camera ready. Right. Okay, this will be on the web page, on the Moodle page from tomorrow. So if you want to see who your compatriots are, you will be able to know from the photograph. Okay, now this is the introduction to the course, in the way of some introduction to the course. And this section, section 1.1, talks about how renewable energy has come about. I think you all know that. All right. What is the place of renewable energy in our life today? All right. And how it is growing compared to other forms of energy. Now, there are lots of resistance in the use of fossil-based energy system, fossil fuel-based energy system. And I don't need to tell you why. You all know that, all right? It produces carbon emissions and acid rain and whatnot. Now, this set of slides were produced by my former PhD student. He is now working at Deakin University. He's a senior lecturer there. I have taken a few pages from his material, and I think he brought it up quite well. Okay. So I'll cover a few pages from his material, and then we'll go to an overview of power electronic systems, okay, that are used in renewable energy systems. Now, so if you do this first section, 1.1, you'll be able to learn about the impact of renewable energy and about the growth of renewable energy till 2016. The situation with energy produced from fossil fuel, burning fossil fuel or natural gas are well known. Australia for its energy production uses coal and gas for nearly 70% of its energy. Okay, now that's way too high in the modern situation where the climate is warming up. Okay, now fossil fuels are the primary contributor to greenhouse gas. I mean, you must have heard all these things before. I'll just try to reinforce or make the connection to the purpose of this course and where the power electronics help in the process. Okay? Now, power industry, utility industries, they produce a lot of carbon dioxide, goes into the goes into the atmosphere and changes the climate. And the climate change can produce stresses on the systems that are used. All right. If the temperature goes up, the efficiency of energy production goes down. All right. Ultimately, it's the thermal cycle. Okay. So more carbon-based, fossil fuel-based energy more climate change, and more inefficient energy production using using fossil fuels. So it can be a vicious cycle. All right? The vicious cycle means something that fulfills its existence and go up in a negative sense. Okay. So scientists are saying this, and all over the world, but some politicians, of course, don't believe that. Okay, don't believe their own scientists. Okay, the politics is such that for every political organization or a person in a democratic society, there must be an opposition. All right? So if you believe in something, there will be other people believing the opposite. Otherwise, they cannot justify their position. So that's how politics works. But overall, over the whole world, scientists are in agreement that fossil fuel burning or energy generation based on fossil fuel is increasing the global temperature and putting us in this vicious cycle. All right, one causing the other to go astray. Okay, if you cannot stabilize it, then one day things may go out of hand. Okay, so now how CO2 emissions have grown over the years, and economists and politicians everywhere are aware of this, and they are trying to sort of find a track that will reduce this and hopefully make it stable at 2000 levels and so on. I believe that it is possible to bring it even down. I'll tell you why later on, how. If you look at the carbon at a place in Hawaii, Mauna Loa Observatory, this place is a bit far away from industrial centers like USA, Europe, China, and so on. So the emissions that you measure there could be representative of, representative of the average situation, all right? By the time the emissions reach Hawaii, the peaks and troughs have been averaged. So that was the idea of choosing that site, all right? So you can see that carbon has increased in this way, and the next slide, I think, will also show you the global temperature, average global temperature, how it has gone up. And if you look at that chart, you cannot argue with it. All right? You cannot argue with it that it is not happening. Okay. Right from the beginning, right from this time, where the energy usage was pretty low all over the world, to this time, you can see how the global temperature have risen. Why did it come down here? Don't ask me that question, I don't know. All right? It must have been the fluctuations within the fluctuating band, but this is not within a fluctuating band. All right? It is real. Now, this is a scenario of Australian energy production, of Australian fuel use scenario. In here, nearly 70% of energy is obtained through coal, burning of coal and gas. Sorry, coal. And if you include gas, quite a lot. All right? And they all produce emissions. Now, if you look at this figure, there are some countries where, or there are some areas where the energy production rate has stabilized. All right? But there are some places, if you look at these ordinates, it is growing up. All right? And these are countries like China, India, and so on. They're relatively lower developed countries. Okay? The fact that the countries that have stabilized, they still produce a huge lot of emissions, but the emission trend is growing. Okay, the use of energy through carbon, the total energy usage is growing, and it will grow. Countries like India, Vietnam, Pakistan, there are many other countries, Indonesia, which are quite populous, and the number of and the energy usage is still quite low per capita, and their politicians and economists are working very, very hard to raise their lifestyle or standard of living, so energy will be produced more and more. Okay, so if this trend continues, then we will be in real trouble. So, what are the, if you can produce energy from non-fossil fuel sources, then you can prevent that runaway situation. And one area is wind, and the other area is solar. Hydro is expected to be totally exhausted, means all the available hydro resources will have been exploited within the next 20 years. All right. In China, the Three Gorges Dam. Then in Brazil, next to Brazil, which country is that? Itaipu Dam, that has harvested quite a large amount, and Vietnam is using that. Laos is doing that. And in Africa, there are also lots of renewable energy production from hydro, in India also. But most of the countries are coming to exhaust the resources. Okay, so tidal and geothermal are, they have technological difficulties. Biomass is also not in big amount. So the main two ways in which renewable energy can be had is wind and solar. Now, this figure, or this chart, shows various energy production methods and how they have grown from 2015 to 16, and the positions of various countries in terms of their renewable energy development are given in this slide. So you will know which countries are in which place and what they have produced from renewable energy up to 2016, and how, if you compare between 2015 and 16, you can see immediately that it is growing by nearly 10%. Now, capacities. Current capacities, that's what it's shown here worldwide. These are the current status in 2016, all right? How much solar, how much winds, how much biogas, power from biogas, and so on. Now, what I have come across, or I think many of you also know, that the solar resource can potentially replace all other sources. All right, this total solar energy that is available, or can be available on this planet, can run the economy of all the countries. All right, even when every country is fully developed. Okay, so if we move to solar, then someday 100% can be renewable. All right. America is a highly industrialized country, but the solar potential that it has, it can run the whole country. All right. The wind energy available in Atlantic can run the whole United States. Okay. Now, the question is, how do you get the wind from the middle of the ocean? Of course, you have to make some conversion from wind power to liquid nitrogen, perhaps, and then transport it to shore or export it to other countries. Australia has vast amount of solar resource and wind resource as well. If solar energy is converted into liquid nitrogen, it can run, not only run itself from that, but it can also export huge amount, all right, much bigger than what Middle East exports in terms of oil. So these are the ultimate possibility. It will not come so soon, may not come within your lifetime, not to say about mine, but it may not come in our lifetime, but world should be heading that way. And one day, coal and gas will run out anyway. So I'll leave it at this point, this slides. There are some technologies, description of technologies in this page. If you read it in your own time, you will understand what are the possibilities of and how various types of technologies are used to produce renewable energy. So I'll stop at that point on this set of slides. Any questions so far? One on what we have just covered. What we have just covered is a statement of the realities and about polluting ways of producing energy and what the world can become if we harness more and more renewable energy sources. And solar and wind are the main two sources which can meet the demands of the whole world. All right, eventually they're all harnessed and introduced to the grid, and with the efficiency and reliability that is required. All right, the efficiency, and so how to harness that energy, put it to the grid, how to achieve the efficiency, how to achieve the reliability. These are the things we are covering in this course. Okay? All right, so I'll take a break at this point. I had one lecture here about an hour ago, or more than an hour ago, just about 2 hours ago, and then I'm doing 3 more hours. So I'll have to take a bit of rest, 10 minutes, just 10 minutes. Or maybe I can put it here and then copy.
And you can send it to offline and just to PowerPoint.
Where is your drive?
Yes.
No, that's mine. That's
This
mine.
yours?
Yeah.
Maybe this one?
No. That has not been recognized.
I choose another one.
I don't think it is recognized. This one?
Yeah.
Oh, okay. Which one?
This one? Yes. Interesting.
Okay, so I paste it here, okay?
Yeah. Just over here. Yeah, okay. Thank you.
Now, the overview
Yeah.
in the different locations. Sorry, not the overview.
Okay, thank you. Thank you. Yeah. Thank you.
Okay.
Thank you.
Okay. I'm ready to start again. While we had that 10-minute break, one student came to me to ask my opinion, and his question was that renewable energy is still a very small proportion of the total energy. All right. So, what is the job prospects for all these students? And what I could say is that energy farms based on solar and wind there are many startup companies coming up all over the world. And two of my recent PhD students, very recent PhD students, were recently absorbed in one of those companies in Australia who are producing energy from solar and wind, and they're selling it to the Australian grid. All right? So that trend will grow bigger and bigger, I think, although it is small now. But I feel that this will not remain small. That's the answer I gave him. If you ask questions like that, it is better to ask so that everybody can hear, all right? Ask the question and the answers. All right, sometimes better answers will come from you yourself if you have any experience of in the industry or some other place. Okay. So ask questions if you like, and we will try to, that will make this lecture a bit more livelier. Okay. Now, what I'm going to give you in a short few slides is the overview of power converter used in renewable energy systems. Overview of power converters for renewable and distributed energy system. In the Moodle page, this section comes as 1.2. Okay, section 1.2. What I gave previously was section 1.1. And so when we finish this, you will understand the operational characteristic of power electronic converters for wind and solar generation and energy storage systems. Understand the power converter control system structure in renewable energy systems, but still an overview, not going into the deep of this topic. Okay. In renewable energy systems, these are the converters we use. DC to DC converter. For PV, we mostly use boost. In some cases buck boost, but not buck, all right? But so the boost converter or buck boost converter may collect energy from the solar after maximum power point tracking and so on for all the conditions of the solar arrays. The energy will go to a capacitor, all right, and then it can go to the grid, all right. If it is locally stored, then you need a buck converter, buck and a boost converter to put energy into into a battery, all right, from the PV or wind system. And when the grid demand or the demand of the load has fallen, then the excess energy can go to the battery, all right? And then at other times, the battery could then supply energy to the grid or to standalone loads. Okay, so all three types of converters are used in renewable energy systems. SEPIC converter is also used. It's a way you will see later. We normally don't cover that in undergraduate course, but SEPIC DC-DC converter and CHUK DC-DC converter, those are also used to generate power supplies which will drive the electronic circuitry. Bidirectional DC-DC converter we will cover. As I said, buck and boost converters can be combined to produce a bidirectional converter to put energy to the grid or energy to the grid and also energy to the battery for local storage or a centralized storage, and then from battery to the grid and so on. Okay, these bidirectional converters interact with grid or the load and the renewable energy systems. I think you all know that there is hardly any requirement for energy storage in a battery to go to, for example, a wind turbine. Wind turbine rotates itself by the available wind, so you don't need to drive it, and there is no reason to drive any solar array. Now, AC-DC converters, a lot is used in wind energy systems, all right, diode rectifier for small scale, a few kilowatt system, all right, where the size of the wind generating station is not big. There is space available, so you may not need, you may be okay with a diode rectifier, but nowadays that diode rectifier comes with power factor correction so that the size of the wind generator becomes smaller. Okay, thyristor control rectifier are used for high voltage connection if the solar farm is many megawatts, all right? There are gigawatt solar farms have been built and running in China and in India and so on. So for large stations, renewable energy power station, you would need thyristor controlled rectifier to transport energy to the grid, okay, through an HVDC system. That will be covered in, I think, in week 7. And then there is PWM rectifier, which is diode rectifier in parallel with an inverter. Okay, we will show the structure later on, but we call it pulse width modulated rectifier. Again, it is like diode rectifier with power factor correction. However, if we have PWM rectifier in a 3-phase system or even in a single-phase system, we can control the power flow in a much more elegant and controllable way. All right, so that is the requirement for PWM rectifier. And then, of course, there is DC to AC inverter for interfacing to wind, and from wind to, we use a PWM rectifier to produce DC, and then the AC inverter produces the AC, 50 hertz AC, to connect to the grid. All right, so we'll cover that inverters in a bit more detail, DC to AC converters in a bit more detail that we do in a first course. And then there are multi-level inverter, which will also be covered, which we'll go through. I do that? Okay, so if you look at the situation in a wind turbine power generating station, this is a small scale system where there is a machine which converts the mechanical motion into electrical energy. The wind incept on the blades lets it rotate, all right? And then the AC produced goes to a capacitor, all right? And you then boost it up to another voltage, because this voltage may be variable and it is normally lower than required to connect directly to the grid. So you boost it up to another level, and then you have a three-phase inverter to connect to the grid. All right. Nowadays, the transformer is no longer used. The three terminals of the inverter are directly connected to the grid. If it is at, especially when it is at low voltage utility level. Now, when it comes to bigger system, we normally adopt this scheme. We have a three-phase rectifier, which we call PWM rectifier, which produces a voltage across here, and power is extracted from the wind turbine, and it goes through a filter, and then we produce a voltage here, and that voltage is higher than the peak-to-peak voltage here. Okay, so we call that voltage source rectifier or PWM rectifier. And then we have an inverter producing three-phase sinusoidal output, and we connect to the grid. All right. So we look at this circuit, which is called boost converter. There is also, if you parallel switches here, the 6 switches, so this is like a diode rectifier plus 6 switches. So it looks like the same circuit as that, but this part acts as a rectifier, this part acts as a inverter. So we would be looking at how to control these and how to control these, all right? To extract the energy and so on. And the control of this inverter can also be made such that we can feed real power and reactive power to the grid. Okay, when you feed reactive power to the grid, it affects the voltage, all right? And when you put real power, it affects the frequency and so on. Okay, so you may have to inject both real power and reactive power, depending on what the system impedance is. So controlling this converter with a certain power, real power and reactive power reference to put to the grid is something we will look at, all right? Similarly, this rectifier should extract power from here, all right? But the requirement here is to produce unity power factor situation here. That means the voltage and current would be in phase and sinusoidal. That is not possible in this case, all right? This machine or this generator will not operate at close to unity power factor at all all right, the power factor will be quite poor. And if power factor is poor, you know that the current supplied is higher than what it can be, all right? So if you can reduce, or if you can run it at unity power factor, then the current drawn per unit of per kilowatt is the minimum, all right? So the attention here is how to run the machine with unity power factor and extract power. Okay, normally we run this converter with a certain power reference and 0 reactive power reference. All right, if you put 0 reactive power reference, then it becomes unity power factor operation. Okay, but for this converter, we may have to have a power reference as well as reactive power reference. The power reference here is the same as the power reference there, all right, because the power that comes from here will be transported, all right. If you transport less power than what you receive, then the capacitor voltage will go up, all right. So power balance is an inherent requirement, okay. Otherwise, the capacitor voltage goes up indefinitely. Okay, so that kind of issues, how we handle them, that's what we will cover. Now, there is another type of converter systems. It may look like the same as you saw previously, but in this case, this is a self-excited induction generator. The previous cases were mainly PM synchronous generators. All right, these 3 terminals are in the rotor actually. So you are controlling the operation of the induction machine to generate power, all right, by running the induction machine in the in the second quadrant, so that it produces energy, all right. So, this is still in the stator, but using this capacitor, which is for storing the energy, and some of this capacitive energy, one can allow this induction machine to self-excite, all right? Induction machines don't have any excitation in the rotor. There is no inherent magnetic field, so it cannot generate, okay? But if you can supply this machine with a flux-producing current in the rotor, by sending a flux-producing current so that a field is established, then the machine will generate, okay? So we will be looking into that as well. And then there is another kind of induction machines where the excitation can be in the rotor, all right, not in the stator. Stator gets connected to the grid directly, but we have a back-to-back. This is this is inverter, and this is PWM rectifier. The role has reversed. This draws DC power from the grid with unity power factor and develops a voltage across it. And this inverter then produces current in the rotor, which excites erga field. All right, and then the machine will act as a generator. Now, in this scheme, the converter rating is less than 1/3 of this converter ratings. These 2 converters combined handles only a small amount of power. All right, much less than these converters require. So this has been used a lot in wind power generation stations with induction machines. but the world is moving away from induction generators to permanent magnet generators. All right, as I said earlier, 10 megawatt permanent magnet synchronous generators are being employed, all right, in one unit. Now, in a typical PV arrangement, this is what you have. The solar array, then a boost converter, and then we have a DC supply here. The DC supply voltage is consistent with producing, let's say, 415 volts AC that you have in your household. All right? Now, we normally use boost converter here so that we draw current through the solar array continuously. Boost converters with continuous conduction gives you that capability. Buck converters, if this voltage is higher than what is needed here, then there has to be a buck converter here, which means step down. But if you step down, then for some of the time you are not drawing any current in a PWM cycle, so you are not utilizing the PV array fully. So that's why in most cases one uses a boost converter or a buck boost converter. Okay? So this switch is operated with an MPPT algorithm so that whatever the maximum power is available can go to this capacitor. All right? And depending on the capacitor voltage, we then decide on the current that goes into the local load, if it can absorb it. All right? If it cannot absorb it, if we are producing more power than what the load can absorb, then it has to go to a battery. All right? If we don't have a battery, then we don't convert. All right? There are mechanisms here, parallel diodes and so on, which will mean that not all the available energy is being extracted from the PV array. All right? Only the amount that can meet the local demand will be converted and into AC supply for the load. All right? So this is a typical typical PV energy converter system compared to what we saw in the previous few slides for wind power generation systems. This is another slide where this is still local load, but three-phase. Again, a boost converter, increasing the DC supply voltage here to a higher level, which is what a boost converter provides. And then the rest of the system inverter supplies the local load, and if the local load doesn't require all the power that is available, it can go to the battery. If we don't have a battery, for example, in households, we still don't have battery systems. All right? So if we don't have batteries, then we don't convert, all right, solar energy into DC power here. Now, this is the last category of solar energy supply to the grid. Everything remains the same, except that now it is connecting to the grid. Okay. Now, normally, when it is connected to the grid, battery may not be necessary. All right? In a large solar power station, if the grid is available, then you don't need to store anything in a battery because the grid is the storage, effectively. Okay. If you feed energy which the grid doesn't require, the frequency will go up and the voltage will also go up, and that will be sensed, and some signals will go to the power station to reduce the amount of coal going into the furnace. All right. So we'll look at all of these a bit later on when you go to analyze this circuit properly. We'll leave it. This slide is not very essential. Now, when you have a boost converter and we want to control the voltage, what we normally employ is a technique called pulse width modulation. All right. In pulse width modulation, we have triangular or sawtooth waveforms. We compare that with a reference. This is the comparator. And we produce a variable duty cycle signal at the frequency of these sawtooth waveforms. Okay? If the control voltage goes up and down, the duty cycle of each pulse goes up and down. All right? And with that, we control the switch to increase or decrease the voltage here. Okay? And the voltage that is across the capacitor is a measure of the energy that has been stored, half CV square. Okay? So this is a conventional approach. If you are controlling the voltage here across the capacitor in order to extract energy from the PV array or from the machine, which is the turbine-driven PM synchronous or induction machine. So that has produced the VD, the grid or the wind turbine has produced a VD, and energy from there goes to the capacitor after the boost converter. But the boost converter would normally be run like that with a PI controller to control the output voltage. Having said that, this is a very primitive approach. We normally have a current control as well, the inductor current control, because this type of control will not guarantee that the current is within limits. Yeah?
So, like solar cells are basically like current source rather than voltage source. So, solar panels are basically current source
Yes, yeah.
rather than voltage source.
Yes, yeah.
So, how can we directly connect the inductor?
What do you mean?
Like inductor is directly connected to the current source.
No, the current source is converted into voltage by the capacitor. Each of the solar arrays is a current source, but then that goes to a capacitor. That's not being shown here. That's the ideal source there. Yes, yeah. Okay, and this is a bidirectional DC to DC converter. Suppose this is your DC supply from a wind generator system after rectification, or a capacitor voltage after your boost circuit from PV, all right? Now power can go this way to the battery, or power can go this way and there to the inverter. Okay, then the inverter then supplies to the grid or to the local load. So this is a standard bidirectional converter circuit. Energy can go from the battery can go, at first you put energy in the inductor by turning this on, and then when you switch it off, the inductor energy goes to the capacitor here, or capacitor there. All right, and if you want to put energy from the DC supply, from the grid, or sorry, DC supply from the solar array, which is boosted up, If you want to put energy to the battery, then you turn this one on, then energy will go there, and then when you turn it off, that current will circulate here. So that part is buck converter. Okay, so putting a buck and a boost together becomes a bidirectional power converter. Okay, now this is used quite a lot when energy from households are used to charge vehicle batteries. Now, I think I have shown this slide before. From the capacitor, after the boost circuit, the energy from there can either go to the battery or go through the inverter to the load. And when there is no solar available, then the energy can go to the load by flowing backwards. Okay, so this is a bidirectional buck boost converter. Now, the control of this is a issue or significant issue, because when it is a buck converter, it has a certain Laplace transfer function, all right, two poles. And when it is a boost converter, it has got 2 poles and 1 0 on the right-hand plane. All right, so the controls are a bit different, and for the buck and the boost converter here. So depending on which way energy is flowing, controllers will have to be swapped, okay, on the fly. Anyway, we will look at that later on when we go to that section proper. These are diode rectifier circuits. These are diode rectifier circuits with a boost converter that makes the current waveform sinusoidal here. So this side, AC side, where the energy comes to the circuit, becomes of unity power factor. All right, it could be the AC generator, which is supplied by the wind turbine. All right, wind turbine has the generator. Okay, and that generator is AC output. That can be rectified in this way, and then we can, using the boost converter, we can operate it at a unity power factor. Not only that, we can produce a certain voltage which is consistent with coupling that source to the grid, okay, through an inverter. Okay, now this is also the same circuit. Instead of single phase, it's a 3-phase bridge, and just using one boost converter, one can produce unity power factor here. All right. We will. This circuit is not very much used nowadays, because if it is a 3-phase system, it is already quite substantial. It's not a very small generator. Okay, and this technique with a single switch is not very good in terms of performance of producing unity power factor. Okay, you still have quite a lot of harmonics in the input current. Okay, that's why we go for the other, right? If this is the input, we can produce an output at the same time making sure that the currents are sinusoidal and in phase with the AC supply, which is the output of the wind turbine generator. Okay? And if it is a DC supply available from the solar or from the wind turbine, we can then connect to the grid by using a regular 2-level inverter. All right. We call this type of converter 2-level converter because the terminals, depending on a DC voltage, the terminal voltages here, here, and here, line-to-line voltages can only be of two levels. All right, either VDC, if you switch it on, if you switch this transistor on, this potential is VD. If you switch this on, this potential is 0. All right? Or if you divide it into half and half, it would be plus VDC over 2 and minus VDC over 2. So this is called a two-level converter. And in contrast, this is a 5-level converter. This is again a circuit like this with bidirectional power flow, but each AC voltage waveform here can have, being produced from a DC supply, can have 5 levels, all right, other than 2 levels. Okay, so it can produce more sinusoidal output. And the control, and there are voltage balancing issues and a few other issues which will be dealt with later on towards the end of the course. So there are other types of multi-level converters which are in existence, but very popular of them is the cascaded H-bridge, which will, I don't have the circuit here, I didn't have time to do that, but I'll post it here. Within a week or so you will get the figures here. Dual active bridge is something which is also bidirectional power converter, which involves 2 bridges. It can be called a DC-DC converter with bidirectional power flow. The DC-DC converters that we showed previously can only allow power flow in one direction. All right, the basic DC-DC converters. Now, this will, I'll cover that in detail in week 3 or next week if there is time. So these are the converters that we are going to look at, all right, in the next week. And then we will go into the transfer functions of the converter, the efficiency aspects, and so on. Okay. And in addition to the lecture, in addition to the textbooks that I have mentioned, if you have time, you may also go through these for particular sections. The book number 4 is already mentioned. The other books were not mentioned previously. So if you throw those few slides, you should be able to answer this question. All right, look at it closely. Look at this question. Hopefully you can answer these questions. Sorry?
So what is RES RES?
Renewable energy systems. Multi-level converters are mainly for high power systems because you need if you looked at that, in any multi-level converter, there are many switches, all right? There are many switches just for one leg compared to that circuit. Okay, now the purpose of that is that we don't, if we are connecting power to a high voltage grid, all right, just 2 two switches may not be able to withstand the grid voltage, all right, which could be in kilovolts, 3 kilovolts or even higher, all right. So if you put a few devices in series and give them split voltages between the plus and the negative voltages to switch, then the total voltage capability can be much higher than a two-level inverter.
But in that case, there may be possibility of thermal runaway, right? Because if one of them is not totally identical, then one will have more load than compared to the other.
Okay. It doesn't happen, all right? It doesn't happen. All right. The same current has to go through all of them. That fortunately doesn't happen. All right. When you come to that section, ask that question again. All right. It will be covered in detail later. Okay. They are in series. All right. They're not in parallel. All right. So thermal runaway, I mean, they're all, yeah. Okay, I want to go to the next section if you like. I will take 10 minutes break. All right. So are you okay with those 5 questions?
You told me that permanent magnet, we are moving toward permanent magnet in wind energy. But sir, they are made of rare metals. So if they are, if we move towards them, the most people are going to use them, the more permanent magnets, but we are very limited resource. So how this is feasible?
Yeah, I understand your point, but in spite of that, in spite of the availability,
Because after like we can have like national figure, but after that when the rare metal will get over, then how we going to get that permanent magnet? Once that we have exhausted the rare metals, then we are not able to get into the permanent magnet. Or we can and African countries in Africa they are mining nickel and scandium for nickel. Yeah. Yes, I get the point because they are very high pressure, but I got it like many new countries are not still exploited their resources, and that's why. Yeah. Okay. started it.
Okay, shall we start? The third installment of today's lectures. That's what we are embarking on now. Actually, the course starts at this point. Okay, we are going to cover DC-DC converters, and in doing so, we'll be covering a bit more than what is covered in the first course on power electronics. Now, to help those who haven't done any power electronics before, we have included quite a bit of material here, which comes from the 4614 course, which is the power electronics course at our university. Okay, so, and then based on that, hopefully we can go to the next level of DC-DC converters, which is the dynamic model, the non-ideal components, and so on. Now, we are going to study or review DC-DC converters, which are back boost, or boost, back boost, SEPIC, and bidirectional back boost converters. The basic circuit of the buck converter is in the next page, but in analyzing these circuits, we need to make some assumptions initially. One assumption is that in each converter like this is a buck converter, but you will find that there is an inductor and there is a capacitor. All these two-level converters or second-order converters have two energy storage elements. One is the inductor and the capacitor. And as a result, its dynamic representation has only two poles, all right, because it's a second-order system. Okay. Now, as opposed to fourth-order systems, which we will cover later. Okay. So there is an inductor and there is a capacitor. Okay, so our assumption is that energy flows from the DC source to another DC load, all right? And we assume that the DC load is supplied at constant voltage. So the voltage maintains constant, all right? And energy goes from a DC source, so the current through the inductor will have a DC value. All right, and in each switching cycle, all right, the volt-second balance, that means the LDI/dt voltage across the inductor must add up to 0. All right, there will be no steady DC voltage across it. If there is a constant, if there is a net DC current flowing through it, there will be no voltage across it, okay, in the steady state. All right, and similarly, the capacitor will have no, the capacitor voltage will not build up, all right? That means there is no DC current through the capacitor. If there was any DC current through the capacitor, then the capacitor voltage would keep on going up. Okay, so in the steady state, if this is a DC supply and this is DC output voltage V0, then the capacitor voltage is constant. That means there is no DC current through it, all right? And the inductor has a net DC current, but there is no AC voltage across it. So LDI/dt voltage will add up to 0, all right? Now, how the switch is turned on and off? With the duty cycle that I have discussed before with the pulse width modulator, the switch will be turned on for a while in one cycle, and then it will be turned off for a while in the off cycle. The time during which it is on, we call it DTS. D is the variable duty cycle, and this frequency is constant, the switching frequency. 1/Fs is Ts. Okay. Now, that duration is constant. So if this is dTs, then that must be 1 minus dTs. D is a fraction from 0 to 1. All right? It represents the duty cycle, which means the fraction of time for which the switch is on, and this fraction of time for which a fraction of Ts, during which the switch is off. Okay? Normally, the switching frequency is selected from some other considerations, like how big capacitor we will tolerate, how big inductor we will tolerate, and how much loss we will tolerate in these devices. Okay, so from those points of view, the switching frequency is normally determined. But then the switching frequency is also subjected to what device we choose. If it's a low power, we can use MOSFETs. And the switching frequency can be from 10 kilohertz to several hundred kilohertz. All right? But if it is an IGBT, we don't have much option but to keep the switching frequency around 15 kilohertz, 20 kilohertz. That's all. Okay, so the switching frequency selection depends on what is the voltage and current we are handling, because then the switch is selected according to that. In low power, MOSFETs can be selected. In medium power, IGBTs can be selected. In large power, GTOs will be selected. Switching frequency will be less than kilohertz. So these are the considerations. So in any converter design, switching frequency, which gives you the period, is predetermined. All right? Based on the size of this whole circuit and the losses. Losses ultimately determine the size of the circuit. Okay? It has to allow room for all the losses to dissipate. So that's an issue. Okay, so in a converter like this, we have to assume that the voltage across the inductor, it remains 0. All right? So when you turn the switch on, current rises from a 0 voltage to a 0 current to a highest current. And then when you switch and the current goes to charge the capacitor or to supply the load, and when you switch it off, this current flows through the freewheeling diode. All right, and then the voltage output is 0. And when you switch it on, the output voltage at this point is V of the supply. Okay. Now, the assumptions that we take is what we have already said, that capacitor charge will remain in balance. All right. It will neither increase nor decrease in one switching cycle. All right, and the voltage across the inductor will neither increase nor decrease, or rather the current, the voltage induced across the inductor will not increase or decrease. All right, it will be, the AC voltage across it will be 0. Okay, when the current rises, for example, LDI dt is the voltage across it, and when the current is falling, LDI dt is negative, so the positive and the negative must cancel. Okay, so these are the assumptions, basic assumptions, and also there are other assumptions that we are using ideal devices and components, at least for this analysis. All right, ideal devices means that this is an ideal switch. When it is on, there is no voltage across it. When it is off, the voltage across it is VD. When the diode is off, when you turn this on, diode have to be off. So when the diode is off, the voltage across it is VD. And when the diode is on, because current is circulating, forced by the inductor, the voltage across it is then 0. But we all know that there is some voltage across the diode and it's on, about 1 to 1.6 volts. All right. Similarly, if it is a MOSFET, it can be as high as 3 to 4 volts. Okay, and there is also resistance across the MOSFET. There is resistance in the inductor. There is resistance across the capacitor or in the series capacitor. Series resistance in the capacitor. So we are neglecting all of those so that we can do a simple analysis of these circuits. Later on, a couple of weeks or 1.5 weeks into the future, we will include the voltage across it, the RDS, the inductor resistor, the capacitor resistor, the voltage drop across the diode. We will include all of those to see how efficient the circuit is, all right, how to measure or how to evaluate the efficiency of a circuit like this, and how to find the effect of all those additional parameters on the operation of the converter. Okay, and then finally we will also obtain its Laplace transfer function, all right, in terms of poles and zeros, okay, which will include parameters here and parameters there and so on. Okay, so start with those simple assumptions and then find the characteristic of this converter. So this is the buck converter which we first deal with. The buck means the output voltage is lower than the input voltage. Okay, this is an American terminology. All right, another term for it is step-down converter. Okay, that means we are producing an output voltage which is lower than that, and that's what buck converter does. Okay, so does the waveform make sense to you? Those who have not done power electronics before? The voltage across the switch, if the switch is on, the potential here is VD, all right, because there is no voltage drop here, and then that potential is filtered by this circuit. You may look at it as a filter, but there is more to it than that, all right? And then when you switch it off, the current in the inductor will continue to circulate here, and then the voltage drop in the diode, we assume it to be 0, so the output voltage comes down to 0. Okay, so what is the average output voltage here? The duty cycle times VD. All right, V0 equal to D times VD. Now, but before you go to that, look at the inductor current waveform. We have assumed that the switching cycle is short enough so that the rise and fall is linear. All right, if it was not short enough, then the rise would be exponential, fall would be exponential. Okay, but if the switching period is small compared to the exponential rise and fall times, then we can assume that the current rise and current fall are linear. All right? Now, one more thing to understand is that when you turn it on and the capacitor voltage is V0, what voltage are we applying across the inductor? VD minus V0, right? This is V0 and this is VD. So when you turn the switch on, the voltage across the inductor will be VD minus V0. And what is the rate at which current is rising? What is the rate at which current is rising? VD minus V0 divided by L, all right, that inductor value, because L di dt equal to V, all right, and V equal to VD minus V0. So V minus Vd minus V0 divided by L is the di dt. All right? So this slope can easily be calculated if we, for a given value of L and Vd and V0. And similarly, during the time when it is off, what is the rate at which current is falling? What is the voltage across the inductor then when the diode is conducting? Huh? No. If the diode is, because when we have switched it off, current is flowing here. We assume that the current is flowing here. Part of it through here, part of it through here. Anyway, the diode is conducting. So what is the voltage across the inductor? It should be easy for those of you who have done power electronics before. Minus V0. Right? That side is positive and that side is 0. Previously this side was positive when this one was. This side was negative because V0 was less than Vd. Okay? So we can also, if we know this time, during this time, we know the slope, which is minus V0 over L. Okay. Now, if the figures that we are seeing here is for continuous conduction mode, that means current in the inductor starts at a positive value and at the end finishes at the same positive value. Okay, that means that it is continuing conduction throughout, the inductor is having continuing current throughout the switching period. We call that CCM, continuous conduction mode. Okay. Now, so we can say that delta IL during on time, Vd minus V0 over L, that's the rate at which current rises. And in time dts, it will rise by this value, delta IL. All right? In time dts, current would rise by that value, which is that much. Okay? And during time t off, the current falls at a rate V0 over L, but negative. And in this time, the current changes and the delta IL must be the same as before. All right? Because current has fallen to the same value in one switching cycle. Okay. So then over the whole cycle, VL dt should be 0. And if you do this maths, all right, VL dt, so LDIL during this time, on time, and LDIL during off time, if you assume that that is 0, then from there you get this equation. V0 over Vd equal to D. All right? So the output voltage can be controlled linearly by varying the duty cycle D, if you can assume continuous conduction. All right? Now, so with continuous conduction, V0 equal to D Vd. All right? And remember that we had said that the power must be, whatever power is drawn from the DC source, Vd, must have gone to the load side, V0, and no power has been wasted. All right? Because the switches are ideal, the inductor and the capacitors are ideal. Okay, so from power balance, if you say VD-ID equal to V0I0, then you get this relationship. All right? So with continuous conduction, we get this relationship, which means that the output voltage is proportional to the duty cycle, which is a linear function, which means that we can control the converter very well from linear control theories, because V0 over Vd is D, which you can treat it as a constant. All right, so the gain of the converter is a constant. Okay, so as D changes, the gain changes, but a constant gain. Okay, and V0 doesn't depend on any of the other parameters. Doesn't depend on the load, for example. All right, V0 is determined entirely by the duty cycle. So that means the control is straightforward using linear control theories. Okay. In the previous set of slides, I showed a pulse width modulator and a sort of PI controllers and a voltage regulator and so on. So in those PI controllers, we are dealing with, or at least for the converter, we are dealing with a constant gain situation. All right? How do we define, if this is output and this is input and this is D, if you said delta V over delta D, that's the gain, all right? Output voltage rises linearly with D. Okay, so if you take a slope, the slope is constant, so the converter has constant gain. All right, that's what it means. Now, that is not always the case. The operation can be discontinuous. Okay, that means that happens when the current output is low. Okay, if the load resistance increases to such a high level that the current here is quite small, then the current in the inductor will be discontinuous. It will not flow for the whole time, all right? It will not flow for the whole switching period. All right, because if there is no demand for the current, because the resistance has increased or perhaps become open circuit, then there is no need for the inductor current to flow. Okay? The inductor current flows if it means that it has a DC value, and that DC value times the output voltage will mean that there is an output power, but that output power has nowhere to go, all right, because the load resistance has increased. So in that situation, the converter will become discontinuous conduction, all right? So what happens at the boundary is this situation. That means the current starts at 0, and during DTS, current rises at that rate, Vd minus V0 divided by L, goes to a maximum value, and then from that maximum value, at the end of the duty cycle, it falls to 0. And then the same cycle repeats. So this is on the verge of discontinuous conduction. All right, the load has increased to such an extent that the inductor current at certain point for a certain load will become like this, that it starts from 0, falls to 0. All right? If the load resistance increases further, or rather the load demand, it reduces further, then the current will be discontinuous. It will be going up for a while, and then it will fall like this to 0, and then it will remain 0 for remainder of the circuit, or remainder of the cycle. All right? That's called discontinuous conduction. So if we have discontinuous conduction, which is the situation, it will come later. If we have discontinuous conduction, the current waveform will be like that, and we will have certain problems with converter gain. So before we do that, we go through the motions here, and we find what is the boundary condition. All right? When the load has reduced, or rather the load resistance has increased to such an extent that the converter is on the verge of discontinuous conduction, meaning on the boundary, then the current waveform is like this. And if it is a triangle, its average value is half, the peak. All right? Of a triangle, the average value is half. The load current is the average current, right? The load is drawing the average current. So if the load draws a current less than this average value given by the IL max at the boundary of continuous and discontinuous conduction, then conduction becomes discontinuous. Okay? So anyway, at this point in time, or in this operating condition, what is the value of IL max? All right? ILB equal to half of IL max. All right? And that half of IL max is half of Vd minus V0 divided by L. That's the rate at which current rises, and this is the turn on time, which is dTs. So you get this value for a given d, which is the I0b. So current waveform for operation at the boundary has to be like this, and if we know Vd and V0, then I0b will be found. Okay? Now, I0b can then be written, this equation can be written like this as well. Okay? And ILB will be a term in it, which will be defined as Ts Vd over 8L. Now, what it means is that there is a certain band. If the load current reduces below that, all right, remember that this is a function of d. If the load current reduces below that for a given d, then current is discontinuous. But if the load current is higher, then current is continuous. All right? If the current is continuous, then the output voltage is determined by d alone. Okay, but if the current is discontinuous, the output voltage is not determined by d alone. Okay? From this equation itself, we can define that, and this equation will plot a graph like this, and if for a given d, if the ILB or average inductor current is for a given d is more than that level, then conduction is continuous, and the converter characteristic is determined simply by d according to that equation. V0 over Vd equal to d, constant gain. Okay? Now, okay, so now see when does current becomes discontinuous. All right? We can, for a given load, all right, this is the average current at the load. All right? If you look at the the inductor current, there is a current which is going up and down, but it has got an average level. The average inductor current goes to the load, all right? Because the capacitor cannot have an average DC current. Then the capacitor voltage will keep rising. Okay, so we can, for a given load, V0 over R, all right, the current rise in a cycle is delta IL over 2, all right? So if you look at this figure, half of delta IL is the total rise during this time, and this is the total fall, and they are equal. So delta IL over half plus the average current through the inductor is the IL peak, is the IL max of the inductor. Okay. So IL max is the load current plus half of the ripple or inductor current change, and then IL has been written previously by this equation. So you add that as delta IL over 2. And IL min is again the average current minus delta IL over 2. And after you put delta IL for this cycle, this period, it becomes like this. So if you then say that the minimum current will be 0, which is the case for operation at the boundary, all right, then you get this expression that you set this equal to 0, and then you equalize that with that. And then you come up with this expression that LFS min is given by that. All right? So which means that the switching frequency and the inductor has an intertwined relationship. Okay? You can change one, and then the others will be determined accordingly, so that up to a minimum load current, the converter operates with continuous conduction. All right? So normally we would use this formula for a given switching frequency. The inductor value will come from here. All right? If the inductor is bigger than what this equation says, then current will be continuous. If the inductor is larger than what that equation finds, if the inductor is smaller than what this equation says, this inequality equation gives, then current would be discontinuous. So I will take this up later on when you go to look at the operation under discontinuous conduction. At least now we have known what is the minimum inductance that we require so that current remains continuous. If current remains continuous up to the minimum load, up to a certain load, then the converter characteristic is linear. And we can control the converter with linear control theories. Okay? We'll leave it at that and then deal with the discontinuous conduction problem later. But before that, we go to the capacitor selection. All right? What is the capacitor current like? What is the capacitor current like? Capacitor current should be AC, because DC current in a capacitor, in that capacitor at the output side will mean continuous rise or continuous fall of voltage. We are assuming that the capacitor voltage remains constant. Okay? So the capacitor current will be like this. During turn on, it will go up, and during turn off, it will go like this. So the net capacitor current is 0. All right? So if we know the current waveform in the inductor, which is like this, then that's the time during which the capacitor is charging, and that's the time during which the capacitor is discharging. All right? So from there you can say if we integrate that area, that's the delta Q, and delta Q over C would be the delta V0. Remember, we started with the definition, with the assumption that the capacitor voltage V0 was constant. But it cannot be constant because it is getting current sometimes and it is discharging current sometimes. So around a constant value, the voltage is going up and down all the time, all right, in every cycle. What it means is the capacitor voltage ripple should be contained, should be below a certain value. Okay, so if we specify that the V0 voltage will be less than 1% of the nominal V0, then we can find the required capacitance from this equation. Okay, so that's how those two values of inductors are found. So, sorry, the inductance and capacitance are found. This gives you the L, and for the minimum load, means the highest resistance, all right? And this gives you the C for the acceptable capacitor voltage. Okay, so that's how we obtain the parameters of that converter. Okay. Now, if you look at the output voltage of the output voltage here, which is supposed to be V0, but the voltage at this terminal, across this terminal, is like this. So if you subject it to a Fourier analysis, assuming that this is a filter, LC filter, it will have a Fourier spectrum like that. All right, V0 will have a DC value and a Fourier and a ripple at that frequency, and then at that twice Fs, this is at the switching frequency, and so on. All right? That's what the output voltage waveform at the input of the LC components is. So if you do a border diagram, it will look like this. L and C makes a resonant circuit. All right? So it will be a bit of a peaky border diagram. This is frequency and this is magnitude. Okay? If you want to design the converter from frequency response alone, you would find that the cutoff frequency of that filter should be that, all right? And at the cutoff frequency, the gain of the converter should be at least minus 80 dB. All right, then the ripples across the capacitors is bearable. Okay, so that's another way of finding the capacitor and the inductor values. Okay, so then what happens if the conduction mode is discontinuous? In converter systems, in the buck converter systems, we always try that the converter never operates in discontinuous conduction mode. All right, in power supply circuits, across the capacitor there is a dummy resistance there. All right, so that the minimum load is drawn always. Okay, which is inside the power supply box. Now, so there would be a dummy resistor here, so that the minimum load is always more than for this situation. All right? But anyway, theoretically, if current becomes discontinuous, then there is some analysis which I will leave you to do, and those analyses will show, it's not difficult. If you have understood the waveforms and how we analyze this circuit, you will easily find that with discontinuous conduction, the converter characteristic is like this. V0 over Vd is given by this formula. All right? So it is quite nonlinear. It is no longer d here. It is 1 plus root over 1 plus 8 LFS over d square r. The V0 to Vd relationship is determined by d, but also by load, and also by switching frequency and inductor and so on. Okay, assuming that switching frequency and the inductor remain constant, all right, after the circuit has been built, the inductance and the switching frequency are not going to change. Okay, what will change is the duty cycle and the R. Okay, so V0 to Vd ratio is determined by the load as well. Depending on how much load, the ratio between V0 and Vd changes for the same D. Okay? So it becomes more difficult to control the converter if we have a V0 to Vd relationship which is rather nonlinear. It has a d square term here. Nevertheless, there is a root over, but it depends on the load as well. Okay, so to control the converter with such gain is quite difficult. Okay? If you go back to that circuit, which those of you who have done 4614 will probably have found the relationship between output voltage and D, which would be quite nonlinear. All right, the output voltage versus D, instead of being determined by D alone, it will fall, or it will fall quite drastically, or rise, the voltage will rise quite drastically if the converter becomes of discontinuous conduction. Okay, so what I'm saying is that if the converter goes into discontinuous conduction, the control becomes difficult, and therefore there is a tendency to select L and the load such that the converter will never go into discontinuous conduction in order to avoid that problem. Okay, so I'll complete the buck converter analysis here. I have not gone through the whole analysis of discontinuous conduction mode. I only highlighted the formula between V0 and Vd, which is connected in a very nonlinear way with the D and the load resistance. Okay. Then we will deal with, how much time do I have? Okay, 10 minutes more. Then we'll deal with review of the boost converter. How does the boost converter operates? The boost converter is a circuit where the supply voltage is Vd, like the PV array output voltage, all right, or the rectified voltage from the generator, turbine generator, PM synchronous machine, and so on. So that's the voltage here. All right, and then you have an inductor and a switch and a diode and a capacitor. This forms the boost converter. All right, L, D, and the T. These three items produces the boost converter. Boost converter means that V0 is higher than Vd. All right, that's the meaning of the term boost, that it boosts the voltage up. Okay. Now for PV arrays, this is the circuit that is mostly used. Okay. After the PV, this is the circuit, first circuit. Okay. And then the inverter and so on. Now, how does it operate? Again, we start with a PWM duty cycle where this is DTS and this is 1 minus dTs. All right? Pulse width generator, pulse width modulator will produce that. Now, when the switch is on, what happens to the inductor current? Current will rise like that. Let's say it starts from a non-zero positive value, and then it will rise to a maximum. And then when you switch it off, what happens then? The current that was in the inductor will then flow in this circuit. All right, this switch is off, so the inductor current I max will start to flow here. Some of it will go here, some to the load. Right? Now, again we assume that this voltage V0 is larger than Vd, and it is constant because the capacitor current, the DC capacitor current is 0. The DC current through the capacitor is 0. All right? And in order to have a constant rate of power flow, the current here would be DC, all right? Which means that if the current rose by a certain extent, it must fall by the same extent during when the switch is off. All right, the current rose by this extent when the switch was on. All right, it rose at a rate Vd over L. That's so Vd equal to L di dt, and Vd over L is the di dt. So this rate, di dt, the slope, is determined by the inductor value and the supply voltage. And at that rate, current will rise. And then afterwards, when the switch is turned off, at what rate current falls? It will be Vd minus V0 divided by L. Current would be forced to flow through the diode. The voltage here is 0 while the diode is conducting, and the capacitor voltage is V0, and this voltage is higher than Vd, so current will fall. All right? And during 1 minus dTs, current must fall to the same value as previously. Okay? Otherwise, there is a DC current here and also an AC voltage across the inductor, which is not possible. All right? Okay. So we then do this volt-second balance. All right. That means the rate of rise and rate of fall, having been defined by those equations, that rate of rise is Vd over L and rate of fall is Vd minus V0 over Vd minus V0 over L, but the respective times are dTs and 1 minus dTs. So if you put that inductor voltage VL equal to 0, that's the volt balance equation, volt second balance equation, then it will be 0, and then this would be the output voltage relationship with D. All right, V0 over Vd is 1 divided by 1 minus D. Okay, if D is 0.5, what is the relationship between input voltage and output voltage? Huh? Huh? Output will be twice the input. If D is 0, it's equal. And if D is 1, infinite. So that means the converter gain can be from 0 to infinity. Practically not, but theoretically. We are talking about theoretically. Practical problems is not shown in the mathematics. All right? So if the D comes near 1, the output voltage is near infinity. Okay. If you plot V0, I may have it somewhere. Yeah, if you plot D versus V0 over VD with continuous conduction, the characteristic is like this. D to V0 relationship is like this, assuming that VD is constant. All right? So the slope of this curve is the gain, and that gain changes with D. All right? So if you operate a boost converter with a D near unity, you are operating somewhere here. For slight change of D, there is an enormous change of voltage. All right? And that is difficult to control. With that, the converter is difficult to control. All right? Because of that, power supply industries operate boost converters in discontinuous conduction mode. All right? Which will be somewhere here. So relationship would be linear. All right? Even with D equal to 0.5, if we operate at discontinuous conduction, the voltage change from there to there would be not be like this. A reasonable change of voltage for a reasonable change of D. All right? That would be the case with discontinuous conduction. But in PV energy systems, the boost converter that follows the PV array is always operated in continuous conduction mode. And in the industry, D has been used as high as 0.85, all right, which gives you about 5 to 6 times the output voltage, all right? But then it is difficult to control, and the controller has to be quite, the challenge for design of the controller is quite high, all right? But that problem has been dealt with, all right? But for power supply industries, we always prefer DC to DC boost converters operating in continuous conduction mode. But for PV industries, we use boost converters in continuous conduction mode, because if it is discontinuous, that means current is not flowing. Discontinuous conduction means current in the inductor is in some part of the cycle is not flowing. All right? So then you are not harnessing the energy from the from the array during that time. All right? So in order to extract certain energy, you are forcing more current output than should be. All right? So that's the reason PV industries prefer to operate the boost converter in continuous conduction mode. Okay? Now the analysis for finding the value of inductor for a chosen frequency, so that we can have, we always operate in continuous conduction mode, can be found by considering the case for boundary condition. All right? And from there, you will find the formula for, where is that? Yeah, that's the formula. All right? Ts is 1 over Fs. So if you write Ts as 1 over Fs, it becomes LFS. So if you select L according to this formula for a given D, then you will be operating the converter at the boundary. All right? But if you choose a higher L, which is given by this formula, then you will operate the converter with continuous conduction. And that's what PV industry requires or prefers. Okay. So I'll not go through that analysis. After having done the boost converter analysis systematically, if you apply the same, you will be able to go through the boost converter inductor selection process. Okay? And then finally, the capacitor selection. How do you select the capacitor? All right? The consideration is very simple. When you turn the switch on, there is current flow here. All right? So, and the diode is off because positive voltage here, negative voltage here, and 0 voltage here means the diode is reverse biased and it is off. All right? So when you have switch T on, this diode is open circuit and the current, load current is supplied by this capacitor alone. All right? There is no contribution from this DC side when you switch it on. All right? So for a given D, if you know the D of the switch, the duty cycle, during 1 minus DTS, during DTS, the capacitor is losing charge. So how much charge is lost during D? That's the voltage. That's the voltage ripple. Okay. So from that, I have given here the relationship between V0 and VD when discontinuous conduction takes place. But discontinuous conduction is avoided for PV systems. Okay, so if the current is supplied to the load, which is V0 over R, and that current is supplied during DTS, so the current times the DTS is the charge that the capacitor will lose during DTS, and if you divide by C, that would be the delta V0, which is the voltage change in a switching cycle. All right? So if you want to keep it within 1%, then you can find the capacitor value. So that's how the capacitor value is selected for a boost converter, and from this equation, the inductor is selected. Okay? So I think we'll leave it at that. And next time we meet, we'll cover the other circuits, which are the buck boost converter circuit, which are the, buck boost and the other circuit.
I'm attending your electric drive courses for undergrad. So sir, on this thing, I received one mail. Sir, on that day you have a class from 4 to 5 over here on Wednesday. And this. So it is clashing with your class, sir. Like you will be over here or there?
No, from 4 to 5 I'm here.
Okay, sir.
I did the drive course here from 4 to 5.
Okay.
And from 6 to 9, this course.
Yes, sir. But because no, sir, I'm not saying that. Sir, actually, on week 2, Wednesday, first year, the electrical department is having this thing. Like you will be over here. Okay.
If you feel comfortable, then you go.
No, sir. So I will be attending class if you are. So it will
That's
be.
only an information session,
Okay, sir.
which you can get in many other ways.
Okay, sir.
Information.
Okay, sir.
All right? That is up to you what you want to do.
So class.
Okay.
Thank you, sir.